I hope everybody has pen and paper, because for Goldfield Quant test, I'll give you a note too. Though the test is written here, however, I'll give you a more detailed, note on this. So if you first look at the slides, it is popular to assume sigma I square is positively related to one of the covariates. Last day also, when we tried to understand what is meant by heteroscedasticity graphically, we found that repetitively we are trying to trace the relationship between residual and explanatory variable, etc. So explanatory variable is coming repetitively in our analysis. And then we discussed several tests up to Glaser test, where also we are bringing xi's in our analysis. Okay. So suppose we are considering sigma I square is presented in this way: sigma square into one of the explanatory variables, one of the covariates, x1i, x2i, x3i, one of the covariates. So here typically we have considered x2i and considering the square of this. The bigger xi we have, the bigger sigma I square is. That is, there is a relationship between the variance of the error term and x2i. So as x2i is bigger, sigma I square will be bigger, because we are considering the absolute values, x2i square. Okay, for last few cases here also, the null hypothesis will be no heteroscedasticity. In other words, it is homoscedasticity. Now here you have to make an arrangement of the data. So what you have to do, you have to sort the covariates with the order of x2i. Okay. So here we will consider that variable x2i, and either in increasing order or in decreasing order, we will sort the variables. Okay, according to their values, increasing order of values or decreasing order of values, we will present the variable in that way. Generally, we consider increasing order. Then what we will do, we will delete C number of central observations, several central observations. So what we will have, starting from the beginning, we will have very small values of x2i. Then there will be, for 10, 15 observations, there will be no values. And then the higher values will start. So there will be a gap between the smallest number we are considering in the first part and the larger number we are considering in the second part, because we are deleting C central observation. For example, suppose if the values are 1, 2, 3, 4 and moving like 100, so I am keeping up to 1 to 30, then I am deleting 20 observations, and then I am starting from 60. So there is a gap between 30 and 60, so this kind of thing. So first I am ordering the observations and then deleting C central observations. So we will have the smaller values of the observation, and then we will have the higher values of the observations. Then we will feed two separate least square regression for the two models. Okay, for the smaller numbers and for the larger numbers. And then we will calculate the residual values. Okay, we will calculate, better to say, we will consider RSS1 and RSS2. RSS1 for the first group and RSS2 for the second group. Okay. Still, if we find there is not much difference between RSS2 and RSS1 statistically, in that case there is homoscedasticity. Because we deleted several central observations, still the residual sum of squares of the smaller numbers and residual sum of squares of the larger number, if there is no statistical difference between these two groups, in that case we consider that there is homoscedasticity, that is null hypothesis will be accepted. However, if we find that there is a statistical difference between the two residual, in that case, two residual sum of squares, in that case, we will consider the case as heteroscedasticity. Okay. Now, to check the significance, we need to fit a statistic. Here we will bring a ratio lambda, which will be the ratio of RSS2 by RSS1. RSS by degrees of freedom, that follows the chi-square distribution. So when you are considering the ratio of two RSS and you are deflating it by their respective degrees of freedom, in that case, you are getting 2 chi-square deflated by degrees of freedom in the numerator as well as in the denominator. So it will follow the F statistic. So this is the logic of Goldfeld-Quant test. So first I am considering a covariate with which my variance is related, and then we are ordering that variable in increasing order of magnitude, deleting C central observations, and then fitting two separate regression models, calculating RSS1 and RSS2, fitting lambda using these RSS1, RSS2, RSS1 and 2 with their respective chi-square, following the respective chi-square will follow the F statistic. So finally, we will concentrate on the F statistic and will take the final decision whether there is any difference between the two residuals or not. So this is the basic idea. The steps are also here. However, I'll dictate you the steps, so please write down, because a few more things in between I'd like to add. And finally, we have to check whether this method has any limitation or not. The first problem actually will be regarding the C central observations. Central observation, this term is very much subjective. To you, the number of central observations may be, 20 central observations. To me, it can be 35. So how many number of observations we are deleting, that is varying. That will vary from person to person. It will depend on my judgment. What will be my number? What or how many observations I'll consider as central observations. So this issue is problematic, and for this matter, many a times, we will not like to use the Goldfeld-Quant test. Logically, the test is very good, very sound. However, the problem is regarding C. If C is too large, in that case, there will be some problem regarding the degrees of freedom. And if C is too small, in that case, it is ridiculous to consider this process and then compare the two groups. So C will be neither too large, too small, and there again there is the issue of subjectivity. So what will be your moderate number to you and to me, and that will be the limitation of this kind of test. So please write down, give heading Goldfeld-Quant test. It is a small sample or finite sample test. Suppose it is known that sigma I square varies with, suppose it is known that sigma I square varies with jth explanatory variable. Sigma I square varies with jth explanatory variable. Let's assume sigma I square is positively related to the variable xij. sigma I square is positively related to the variable xij. The test procedure is then as follows. The test procedure is then as follows. Number one, step 2, write down the things in this way. First step, 1. Reorder the observations in an increasing sequence of xij. Reorder the observations in an increasing sequence of xij. Step 2. Omit C central observations. Step 3. Fit separate regression by OLS. Fit separate regression by OLS to the first and last what will be the number of observations? Both in the first and the last group. If we start with the n observations.
N minus C, N minus C.
Aratrik is telling n minus c, n minus c. Is he right?
I mean, n minus c by 2 or n minus c by 2.
Yes, that will be n minus c by 2. Because total observation is now n minus c and you are breaking it into two groups. So n minus c by 2.
Okay, ma'am.
Write down. Fit separate regression by OLS to the first and last n minus c by 2 observations. N minus c whole by 2. N minus c by 2 observations. Provided of course, that n minus c by 2 exceeds the number of parameters to be estimated. Provided, of course, that n minus c by 2 exceeds the number of parameters to be estimated. Four, let RSS1 and RSS2 denote the residual sum of squares from the two regressions. With the subscript 1 denoting that from, the smaller xij values.
Ma'am,
Yes, Shreya.
step 4 টা একবার রিপিট করবেন প্রথম থেকে?
Let RSS1 and RSS2 denote the residual sum of squares from the two regressions, hyphen. With the subscript 1 denoting that from the smaller xij values. and 2, that from the larger Xij values. Then next line, capital F is equal to just thus capital F is equal to RSS2 divided by first component is n minus c by 2 minus k number of parameters. So n minus c by 2 minus k whole divided by RSS1 divided by, in the similar fashion, first n minus c by 2, that is the number of observations, minus k, that is the number of parameters to be estimated. And this follows if subscript n minus c by 2 minus k, comma, n minus c by 2 minus k. N minus c by 2 is the first component, minus k is the second component. N minus c by 2 is the number of observations, minus k is the number of parameters. Okay, then the last line is same, reject H naught, if and only if your estimated lambda or your estimated F is greater than the critical F. Then add the power of the test will depend, among other things, the power of the test will depend, among other things, on the number of central observations, excluded, number of central observations excluded, and will clearly be small, if C is too large. Okay, so your observation is now n minus c by 2. If C is too large, in that case, there will be a problem regarding number of observations leading to degrees of freedom.
Ma'am,
Yes.
could you repeat after the number of central observations? Could you repeat after that?
Yeah. Number of central observations excluded and will clearly be small. Power of the test will be clearly be small. And will clearly be small if C is too large. So I am repeating the entire thing. The power of the test will depend, among other things, on the number of central observations excluded, and will clearly be small if C is too large, within bracket, so that RSS1 and RSS2 have very few degrees of freedom. Bracket close. Or too small, or too small within bracket, so any possible contrast between RSS1 and RSS2 is reduced. Okay, so this is all about Goldfeld quant test. You will find, workout example in both Madala and Johnston. I think in Johnston too, I think there is a worked out example. So please check all these things. So you can have a several, number of observations. Then it can be told, that delete these observations, and then you can run to separate regression on the first group and on the second group, and then you can find out RSS1 and RSS2 for the two regressions, and then you can fit F test. Okay, so it's very handy numerically too, in the practical lab too. Easily we can do all these things. In practical case it is more easier because it will be easy to sort the things. In case of theory classes, or if you do it using the actually physically we do these things without the machine, in that case the sorting part is a bit cumbersome. Otherwise the things are good. However, if you use Excel, you will be able to easily sort the observations, and you will be able to delete C central observations and run two separate regressions for two group, and will be able to compare the same. Okay, so this is all about the Goldfeld quant test. Any question? So if it is understandable, next we are moving to the last test we are considering here, that is the Bruch-Pagan-Godfrey test. Bruch-Pagan test basically, and later Godfrey brought some changes here, edited the version, and therefore we called Bruch-Pagan-Godfrey test. So we are considering the regression model, standard regression model, yi is equal to beta 1 plus beta 2 x2i. Actually, you can apply it using the two variable case. However, in any text, this is given both for two variable and for more than two variable context. If there are more than one explanatory variable, that context is also covering. So the standard format of the regression is given, which is written in the form yi is equal to beta 1 plus beta 2 x2i, etc. Here we are assuming the variable variance sigma I square. That is a function of several z variables. Now zi can be also xi's. It can be xi's or it can be any other variable. Okay, so sigma I square is a function of several variables. Now if the equation is like that, no heteroscedasticity will indicate alpha 2 to alpha n, all the parameters will be equal to 0. So sigma I square is equal to alpha 1, which is a constant. So this is the idea. So Bruce-Pagan presented the thing as a function of several variables. Sigma I squared is a function of several variables, and then they are fitting a regression equation. Now, if all the coefficients are equal to 0, all the gradient coefficients are equal to 0, in that case, sigma I squared will be exactly equal to the intercept value, which is a constant, and which will indicate homoscedasticity. So how we will frame this test? First, we will have to derive u1 hat up to un hat. Okay, so residual. Again, you have to calculate the residual. First, you need to run the regression, and then using yi minus yi hat, you have to calculate all ei's or ui hat. Okay, so first run the regression, then you estimate your yi hat, then you take the difference between yi and yi hat. This will give you ei or ui hat. Okay, and then it is telling us you have to find out summation ei square by n. Okay, summation ei square by n. So residual sum of squares divided by number of observations. So this we are calling sigma tilde square. This we are calling sigma tilde square. We have to construct a variable pi, which is RSS, not RSS, square of the residual divided by RSS by n, or in other words, sigma tilde square. So what we are doing? First, we are finding the residuals. Then we are finding the value of RSS by n. And once we get this, in the next step, we will calculate RSS by n. Then we will define a variable pi, which is ei square divided by, okay, so E1 squared divided by RSS by n, E2 squared divided by RSS by n. So we will construct pi in that way. Regress this pi, not sigma I square. In the first equation, we considered sigma I square is regressed upon zi's. So here pi we will consider, we will regress pi on z2i to zmi. Okay, and we will find out ESS here. ESS by 2 that follows chi-square with the relevant degrees of freedom. Okay, so instead of calculating RSS at the last step, when we will regress pi on the explanatory variables, this z can be original exci's, it can be set of new variables, will depend on the case, will depend on the particular research problem. Okay, so from this regression equation, we will be able to calculate ESS. ESS by 2 follows chi-square distribution. Now, if we find ESS value is greater than the critical value, in that case, there is heteroscedasticity. Otherwise, there is homoscedasticity. So this is all about the Bruce-Pagan-Godfrey test. Okay. So these are the tests we have in our syllabus at this moment. Any question regarding Godfrey?
Ma'am, PI তে কি লিখেছে?
PI is divided by RSS.
আচ্ছা
This
ম্যাম
guy.
বলছি
UI had
ম্যাম বলছিলাম যে এই এখানেতে আমি এম টা কি হবে আর জেড গুলো কি হবে সেটা কি আমি চয়েস করছি?
It will depend on that. There is a particular problem. You are applying this. So from the research context, we will get the idea. It can be xi, it can be, you know, original xi's, or it can be some variables related to xi. It will depend. If there is any numerical exercise in your test, all these things will be mentioned. Okay. Theoretically, when you will face this kind of problems, generally xi's will be there in place of zi's. Okay. Any other question?
Ma'am,
Yes.
why do we consider the test statistic ESS by 2?
Bruchpagan did this thing in this way, you know. Instead of considering the residual values, here, you know, all these ESS and RSS, they belong to the ANOVA table. The standard practice, for most of the cases, we frame the tests based on RSS. However, there is no problem if we frame the test using ESS. Is there any problem? ESS by degrees of freedom, that will also follow chi-square distribution. Okay.
Ma'am,
Okay, ma'am.
Yes, everything belongs to the ANOVA table. So we can run this kind of test.
ম্যাম
Yes.
ম্যাম ওই সিগমা টিল্ডা স্কোয়ারটা একবার বলবেন কি, মানে ওখান থেকে পিআইটা কি করে আসছে?
Pi is equal to EI square or UI hat square divided by summation UI hat square by n. এইখানটা দেখো, রাইটটা দেখো, Pi we are framing as EI square divided by RSS by n.
ma'am,
The test using the explained sum of square, keeping this point in the mind, if the variables cannot explain Pi, in that case, there is homoscedasticity. However, if the variables can explain Pi, you know, in that case, there is heteroscedasticity. So from keeping this point in mind, we are bringing ESS here rather than RSS. Both RSS and ESS belong to the ANOVA table, so there is no harm if some test is framed using ESS rather than RSS. To give you a sense of, you know, different models or flavor of different varieties, you know, we arranged the tests in this way. There are several other tests. However, if you cover all these, you know, most of the important tests are covered. Okay. Is it fine now?
ma'am,
Yes.
ম্যাম বলছিলাম যে যদি আমি M1 নিই, মানে আমি যদি চয়েস করি তাহলে ওটা কাই স্কোয়ার 0 হয়ে যাবে?
M1 নেবে কেন তুমি?
মানে আমি বলতে চাচ্ছি জেড একটা নিলাম।
নো, কাই স্কোয়ার 0 আমরা করব না, বিকজ আমার কাই স্কোয়ার টেবিলটা শুরু হচ্ছে 1 থেকে, তো 0 করব না। ওকে।
তার মানে দুটো?
হ্যাঁ, তুমি দুটো নেবে।
আচ্ছা,
0 করলে টেবিল দেখতে অসুবিধা হবে। Okay. Generally, we will consider several explanatory variables. As I mentioned, though we are considering the framework in context of two variables, the standard practice is we will consider a multivariate regression. Okay. So that following the standard practice, the test has been written or done. Therefore, we will not consider chi-square 0. Rather, we will start from, you know, chi-square 1. Okay, so this is all about the detection method. In the next step, we need to learn about the remedial technique. If there is heteroscedasticity, suppose you are detecting there is heteroscedasticity. So the next question is how we will proceed. Okay, so from the next slide, we are moving to the remedial measure. Okay, so we are considering the model in the deviation form yi is equal to beta xi plus ui, because, you know, as I mentioned, the entire discussion focuses on beta, therefore we are not considering the intercept. However, if you consider the intercept, this analysis, this analysis can be applied perfectly. So yi is equal to beta xi plus ui, expectation of ui is equal to 0. Expectation of ui square, that is the variance of ui, we are writing as sigma square multiplied with the variable component zi square. So instead of writing this as sigma I square, instead of writing these as sigma I square, I am writing, the variable thing, that is sigma I square, is as if a constant multiplied with the variable counterpart, which is making it variable, where zi is known. Here I missed one zi, where zi is known up to a multiplicative constant, where zi is known up to a multiplicative constant. Now for the covariance, the usual assumption of non-autocorrelation is considered. So expectation of ui uj is equal to 0 for all I not equal to j, x is non-stochastic. Okay, so this is the model with the basic assumptions. Anyone, any problem regarding the model and the assumptions regarding the error term? Is it fine? Yes or no?
Yes.
Yes, ma'am.
Okay, so we can proceed with the OLS estimator like this. Beta hat OLS is equal to summation xi yi divided by summation xi square. And last day we did this thing. Once we get this beta hat OLS, we can write yi as beta xi plus ui, and from there we can have beta plus summation xi ui divided by summation xi square. In the next step, if we consider expectation of beta hat OLS, we are getting this to be equal to beta. So in presence of heteroscedasticity, unbiasedness property of the OLS estimator is not disturbed. Okay, I'm repeating. In presence of heteroscedasticity, unbiasedness property will not be disturbed. The OLS estimators will still remain unbiased. Next, we are considering the variance of beta hat OLS, expectation of beta hat OLS minus beta whole square. Actually, beta hat OLS minus expectation of beta hat. Okay, this expectation of beta hat is giving us beta. This is coming, as you know, this is coming from expectation of beta hat. Okay, now beta hat OLS minus beta from the last slide, it is summation xi ui divided by summation xi square. So I'm bringing summation xi ui divided by summation xi square whole square of that. I'm keeping 1 by summation xi square whole square of that outside, and we are expanding summation xi ui whole square, that is a plus b plus c whole square kind of thing, as well as we are operating expectation. So as we expand the series, that is x1 u1 plus x2 u2 plus up to xn un, if I consider the whole square, I'm getting summation xi square ui square, and also getting summation double summation xi xj ui uj. Operating expectation on ui square and ui uj. Now the second term, that is expectation of ui uj, this is equal to 0 by the assumption of non-autocorrelation. in place of expectation of EI square, you know, I have to bring sigma U square ZI square, because expectation of UI square is equal to sigma U square ZI square. Now sigma U square is a constant, so I can bring it outside the range of sum. So it is summation xi square ZI square divided by summation xi square. So is this calculation okay to all of you? Or should I need to repeat any part?
আমি লাস্ট পার্টটা রিপিট করব।
কোনখানটা?
এই যে এই একদম শেষ যে সিগমা স্কোয়ারটা আসছেটা যেখান থেকে ওই প্রসেসটা।
হ্যাঁ, তোমার example UI square is equal to sigma U square ZI square.
হ্যাঁ হ্যাঁ
এই ভ্যালুটা বসিয়ে দিয়েছি, এইখানে ভ্যালুটা বসিয়ে দিয়েছি। এক্সপেকটেশন অফ UI স্কোয়ার এর জায়গায় we have considered so sigma square, this sigma square that is coming out of the summation ZI square is there. Okay, Narpok?
হ্যাঁ
Now looking at this variance structure, we are understanding it is not the minimum variance that we need to have in context of OLS estimators. Okay, this is no more the okay, this is no more the blue. The estimators are unbiased, however, these are not best linear unbiased estimators. Best property is disturbed. Okay, because for the OLS estimator to have the best linear unbiased estimator, what will be the formula for beta hat variance of beta hat OLS? If you need best, what will be the formula for variance of beta hat OLS? What is in general the formula for variance of beta hat OLS?
Sigma U squared by summation I over I small xi squared.
This is the value. Okay. If this Zi is not there, one xi square will be cancelled with one summation xi square, and you will have sigma U square divided by summation xi square. However, there is this Zi square, you know, and for that matter, you cannot do the things in that way, and you are not getting the value which will give you the minimum variance. Okay. So variance of beta hat OLS is something different from that of the minimum variance, and therefore we can claim that the OLS estimators are not best linear unbiased estimator. Now in this context, we are considering a transformation. Now what is this transformation? Our multiplicative factor was Zi square. Multiplicative factor was Zi square. Okay, so what we are doing, we are taking square root and then we are deflating the original regression by that term. So our expectation of UI square that was sigma square Zi square. So I'm taking this component, square root of Zi square, which is giving us Zi, and deflating, you know, the regression equation by Zi. Vi is also Ui by Zi. So taking square root of the multiplicative component and deflating, you know, actually we are considering 1 upon root over Zi square. Better to say This we are considering as a weight. Okay, and multiplying the entire regression by that weight. We are considering this weight and multiplying the original regression by this weight. Any question? Then we are calculating the OLS estimator. For this weighted model, we are calculating the OLS estimator. So my yi is now yi by zi and my xi is now xi by zi. So the OLS estimator will be given by xi by zi into yi by zi divided by summation xi by zi whole square. So first tell me whether this formula is understandable. Okay. Now before coming to the formula, please look at the assumptions on the error terms too. Okay. My regression is now and this ui by zi is considered as vi. Okay. So I have made the assumptions. Expectation of vi will be expectation of ui by zi. So that will be 1 upon zi expectation of ui. So that will be equal to 0. Now what about expectation of vi square? Can we write this as sigma u square? Anyone? Vi is ui by zi. So when I am considering variance of vi, that will be variance of ui divided by zi square, because for variance you will have square of this thing. So you will have 1 by the variance of ui is so it will be simply sigma square. So variance while expectation of ui square is sigma square zi square, variance of vi is a constant sigma u square. Covariance between vi and vj, that will be absolutely equal to 0. So please check whether you are understanding the assumptions of VIs. It is unbiased, it is giving homoscedasticity, it is giving non-autocorrelation. Now once we get these assumptions, we are applying OLS to the transformed model and getting beta star in this format. The same format, summation xi yi divided by summation xi square. Xi has been changed to xi by zi, yi has been changed to yi by zi, and for that matter, the format is coming in this way. Any question regarding the assumptions of vi and beta star value? Is it okay?
Ma'am,
Yes?
could you explain how we get expectation of vi equal to 0? Because we have expectation of ui equal to 0, but when we operate expectation, how do we get that?
Vi is equal to ui by z. Zi you know as a multiplicative constant. So all Zi values are known to you. Zi is not random at all.
Okay, it is non-random.
Yes.
Okay.
Known up to a multiplicative constant. Look at
ম্যাম
where Zi is known up to a multiplicative constant. Okay, so Zi values are all known. Yes, somebody else had some question.
ম্যাম ওই যে বিটা স্টার যেটা আছে ওইখানে ওয়াই আর এক্সটা হচ্ছে ডিভিয়েশন ফর্মে আছে তো?
স্মল x স্মল y তোমার অরিজিনাল
আর
মডেলটাতে বিটা x
হ্যাঁ মানে হ্যাঁ ওখানে জেডটা কি নর্মাল মানে ক্যাপিটাল জেড না ডিভিয়েশন ফর্মে আছে জেডটা?
জেডটা কেন ডিভিয়েশন ফর্মে থাকতে যাবে? জেডটা তো একটা মাল্টিপ্লিকেটিভ কনস্ট্যান্ট, একটা ভ্যালু, ওটা ডিভিয়েশন ফর্মের প্রশ্ন কোথা থেকে আসছে? এটা তো এক্সপেকটেশন অফ ইউআই স্কোয়ারে সিগমা ইউ স্কোয়ারের সাথে যে মাল্টিপ্লিকেটিভ কনস্ট্যান্টটা ছিল জেড আই স্কোয়ার।
হ্যাঁ ম্যাম বুঝেছি। হ্যাঁ
ওর কোনো ডিভিয়েশন ফর্মের ব্যাপার নেই, ওর ওই ভ্যালু, ওটা একটা ভ্যালু। ওকে, ওখান থেকে তুমি ওয়েটটা ফর্ম করেছো, জেডআইটা তো এসেছে অন্য ভাবে, ওটা একটা ওয়েট ফর্ম করেছো। সিগমা স্কোয়ারের সাথে যে মাল্টিপ্লিকেটিভ কনস্ট্যান্টটা থাকে তার স্কোয়ার রুট নিচ্ছি আর 1/√ স্কোয়ার রুটটাকে আমি ওয়েট হিসেবে ইউজ করছি। So please check the note. Since we are weighting the ith observation by 1 by Zi, okay, since we are weighting the ith observation by 1 by Zi, this estimator is called weighted least square, WLS estimator. This estimator is called the weighted least square estimator, WLS estimator. Okay, so what we are doing, we are transforming the model. How we are transforming? Taking a weight. From where we are getting this weight? We are looking at the multiplicative constant, sigma u square into the variable part. ওই ভেরিয়েবল পার্টের স্কোয়ার রুট নিচ্ছি and 1/√ that square root that we are considering as weight. So since we are weighting the ith observation by 1 by Zi, this estimator is called the weighted least square estimator. So we are applying OLS to the transformed model. What is the transformed model? The weighted model. For that matter, instead of calling this ordinary least square, we are calling this weighted least square because we are applying OLS to the weighted model. Therefore, it is called the WLS, weighted least square technique. Okay. Now, once we get this thing, yi by Zi I am replacing by Vi. Okay. Actually, yi by Zi is equal to beta xi by Zi plus Vi. Yi by Zi is equal to beta xi by Zi plus Vi. So, in place of yi by Zi, if we bring beta xi by Zi plus Vi, we will get, a cancellation between summation xi by Zi square in the numerator and summation xi by Zi whole square in the denominator. So we will get the beta, and the second component will be summation xi by Zi Vi divided by summation xi by Zi whole square. So in the similar fashion we do in case of ordinary least square. We replace yi. Here we are replacing yi by Zi. And as we are replacing yi by Zi by the right hand side of the model, we are getting beta star is equal to nothing but beta plus summation xi by zi into vi divided by summation xi by zi whole square. Since the latter term has expectation 0, expectation of vi is equal to 0. If you take expectation of this entire thing, expectation of beta star, you will get the first term is expectation of beta. Beta is a constant, so you will get beta plus summation xi by zi expectation of vi. Now expectation of vi is equal to 0, so the second term will be equal to 0, and we will get expectation of beta star is equal to beta. So beta star is an unbiased estimator of beta. Beta star WLS is an unbiased estimator of beta. Thus, the WLS estimator beta star is also unbiased. Now we will show that beta star is more efficient estimator than beta hat. That is, WLS estimator is more efficient than OLS estimator. For that matter, we have to consider the variance of beta hat OLS and variance of beta star WLS, and we have to compare the values. Okay. Now we are applying the ordinary least square technique to the transformed model. So variance of beta star will be sigma square, since it is the classical model. You know, the transformed model is the classical model. Look at the assumptions. CLRM, classical linear regression model. Okay. So if you write the formula for variance of beta star WLS, that will be in the form sigma square divided by summation xi square. Now here xi is xi by zi. So you are getting sigma square divided by summation xi by zi whole square. Okay. So while UI were not classical in, because there was the problem of heteroscedasticity, VI is classical in nature. VI is a classical error. And for that matter, if you calculate variance of beta star WLS, the variance formula will be exactly equal to sigma square divided by summation of square of explanatory variable. Now here the explanatory variable is xi by zi, so it is sigma square divided by summation xi by zi whole square. So first tell me whether you are understanding the formula for variance of beta star or not. Is there any doubt, any confusion why variance of beta star WLS is equal to this value? Lakshadweep, Shreya, Oishwarjo. Anyone, any question? Shivani? Is it okay to all of you? Are you understanding it's a classical error and therefore variance of beta star will take this formula?
Yes, ma'am.
Others, you are understanding the matter?
Yes, miss.
Yes, ma'am.
Okay.
Yes, ma'am.
Okay, so if you understand this matter, in the next step, we will calculate variance of beta star by variance of beta hat. Okay, we can prove that WLS estimators are more efficient than OLS estimators. To prove this, we are considering the ratio between variance of beta star and variance of beta hat. Okay. Now look for variance of beta hat and variance of beta star. The formula are given and check the ratio. It will be best if you can do this thing. Or please check this thing and check whether you are understanding. Variance of beta star is sigma square divided by summation xi by zi whole square. This term, sigma square divided by this, as if sigma square was there, divided by this. Variance of beta hat, that is sigma square divided by sigma square into summation xi zi square divided by summation xi square whole square. Okay. So in the denominator, you are getting sigma square. That sigma square will be cancelled with this sigma square, and you will get one summation xi square whole square, which will move to the numerator, and this term will remain in the denominator. So everybody understanding this? Variance of beta star by variance of beta hat? Summation xi square whole square divided by summation xi by zi whole square into summation xi square zi square. Okay. Now the numerator I am writing as, numerator was summation xi square. That I am writing as summation xi zi into xi by zi. So we are getting summation xi square, summation xi square whole square of that. So summation xi square whole square of that I have written in the numerator. Denominator I am keeping as it is, summation xi zi square, summation xi by zi whole square, which was there. I am considering xi into zi as ai and xi by zi as bi. So the numerator is summation ai bi whole square, whereas the denominator is summation ai square into summation bi square. Now, by Cauchy-Schwarz inequality, we can write the summation ai bi whole square divided by summation ai square into summation bi square is less than equal to 1. So if anyone have any problem regarding Cauchy-Schwarz inequality, please Google it and you will get the derivation. What is the Cauchy-Schwarz inequality? We do this kind of inequality at in class 9, I think, class 8, class 9, So maybe you forgot the thing, in that case, please check the formula. Okay, so this is less than equal to 1. So applying this inequality, we can find variance of beta star divided by variance of beta hat, that is less than equal to 1. And that proves variance of beta star OLS is less than equal to variance of beta hat WLS. So, the WLS estimator is efficient compared to the OLS estimator. Both the OLS and WLS estimators are unbiased. However, WLS estimator has the minimum variance property. So, if we use the WLS method, we are getting back MVUE, or the base linear unbiased estimator. So thus, the weighted least square technique is considered as a remedial method to obtain base linear unbiased estimator in presence of heteroscedasticity. If there is heteroscedasticity, if it is detected that there is heteroscedasticity, applying this kind of technique, we can derive the base linear unbiased estimator for the unknown parameters of the regression model. So this is the remedial method in presence of heteroscedasticity. However, the WLS method has some limitations. I mentioned that, we should know, Zi square or up to a multiplicative constant, okay, where sigma I square, or better to say Zi square, is known up to a multiplicative constant. So sometimes what happens, we have no knowledge about this multiplicative constant. Okay, so in that case, we will be not able to apply the weighted least square technique. In that case, we have to go for the generalized least square technique, GLS technique, generalized least square technique. WLS is a specific form of generalized least square technique. Okay, I'll not discuss it in class. However, just I am showing you the name, GLS technique, GLS method, generalized least square method. WLS is a specific type of GLS. So if it is not known, in that case, we will use sigma I, that whole sigma I as the weight. So I'll bring sigma I in the analysis. Here, sigma I is considered as sigma square into a variable component. Now the variable component is known to us, so it is considered in this way. Now if I have no knowledge about the multiplicative factor, in that case, directly using sigma I, we will try to find out the estimated value, so these are the things. We try to find out the estimated values. This we learn in advanced course, what is the general method, because there is some limitation to the WLS technique. However, in your class, we will stop here. We will stop with the WLS. So please note that. Please note that. Take a note. Sometimes we have no knowledge about the multiplicative constant. We have no knowledge about the multiplicative constant, and therefore we will be not able to apply the WLS technique. We will not be able to apply the WLS technique. In that context, we have to use the generalized G capital least square L capital S capital within bracket GLS technique. In that case, we have to apply generalized least square GLS technique. Okay, so this is one problem. And another problem is, look at the transformed equation. Look at the transformed equation. So when you are transforming the equation, yi and xi, or yi by zi and xi by zi are not identical to yi and zi. Now, if your research is with respect to some variables with which you want to finally conclude about everything, in that case, this kind of transformation, zi is another factor. So this kind of transformation may not help you. So sometimes transformation will not give us the economically meaningful result. Mathematically or statistically, we can apply this. However, it may not give us some economically meaningful transformation or economic meaning. Sometimes it will be difficult to add economic meaning to the transformed variable, you know. So in that case too, we need to avoid WLAs and we have to go for general method, generalized least square technique. So as the second point, please mention, under certain circumstances, it becomes difficult to have economic interpretation economic interpretation of transformed variables. Economic interpretation of transformed variables. In that case too, WLS will not be a desirable technique. WLS will not be a desirable technique. Okay, so this is all about heteroscedasticity. Now you need to handle some questions. You can check questions from Madala. One more point you add, you know, one more point you add. That is not the limitation of WLS, you know. One more point you may add as a note. Take a note. Goodness of fit or R square, capital R square, are not at all comparable between the original model and any transformed model. Many a times you will find that students are comparing between the R square of the WLS model and R square of the OLS model. And they are suggesting this model has better goodness of fit, so we will go with this, you know. So this kind of approach you will find under many circumstances. Maybe you will also be tempted to do that. Never do that. The two models are separate models. Their residual sum of squares, ESS, entire ANOVA table will be different. So these models are not comparable at all. So we cannot compare between the R square of the original model and R square of the transformed model, and cannot say whether the transformed model is a better one, the original model is a better one. We cannot move like that. We cannot say like that. Okay. So this point is also important, because for the true false type question or as a part of some question, you may face this kind of issue that you are getting better R square in the OLS model, whereas lesser R square in the WLS framework. So you will retain with the OLS model, you know. So all these approaches are wrong approaches. Okay, so this is all about heteroscedasticity. Next, I'm moving to
ম্যাম
yes.
ম্যাম বলছিলাম যে যে ট্রান্সফর্ম মডেলটা আছে ওখানে ওয়াইআই আর এক্সআই ডিভিয়েশন ফর্মে আছে।
In the discussion of heteroscedasticity, I have considered the model without the intercept term. So, you know, that model is, you may consider the model as the deviation from model, or you may consider the model without the intercept term. No problem. However, if you model with the intercept term, all these applications will be applied in the similar fashion. So you can redo the exercises considering the intercept term. No problem.
ম্যাম তার মানে আমি এমনি ওয়াইআই কেও জেডআই দিয়ে ভাগ করতে পারি, আবার ডিভিয়েশন ফর্মেও জেডআই দিয়ে ভাগ করতে পারি।
Alpha by Z intercept term.
আচ্ছা,
ঠিক আছে, ওটাকে তুমি আলফা প্রাইম নাম দিয়ে দিলে, you will be able to do that. ওকে, ওখানে তুমি দেখতে পারো একটা মাদালায় একটা এক্সাম্পল করা আছে। এক্সাম্পলটা ওই WLS এর লিমিটেশন, ইন্টারপ্রিটেশন এগুলোর কনটেক্সটে বলছি। একটা মডেল this is the original model, standard model. Okay? আর sigma squared, suppose sigma I square, that is tomar, this is the structure. So when we are taking the weighted model, transformed model, it will be like this. Okay, so in the original model, alpha was the intercept and beta is the gradient. In the transformed model, when we are regressing yi by xi on 1 upon xi, in the weighted model, beta is becoming the intercept and alpha is becoming the gradient. So these are two separate models, you know. Interpretation of alpha and beta are just changing. In the original model, they were, you know, alpha was intercept, beta was gradient. In the transformed model, beta is the intercept, alpha is the gradient. You know? So all these things may appear. So do not compare the transformed model with the original model. Treat these two things as two separate regression equations. Okay, Darpok?
ইয়েস ম্যাম।
However, not all sigma I square is equal to sigma u square zi. So you can have sigma u square zi square as we considered. So in that case, the transformed model will be yi by zi is equal to alpha by zi plus beta xi by zi plus vi. This will
এই এখানে ওয়াইআই আর এক্সআই গুলো ডিভিয়েশন ফর্মে নেই তো, মানে এমনি ক্যাপিটাল ফর্মই আছে, তাই তো? এটাই জিজ্ঞেস করি।
দেখে মনে হচ্ছে
না না ম্যাম, ওই যে আপনি যে স্ক্রিনটা শেয়ার করেছিলেন ওইখান থেকে মনে হয়েছিল যে থাকতে পারে কিনা।
not always. We can consider a model, you know, where there is no intercept. No problem. Okay. So you can consider that looks like a deviation form. You can consider the deviation form model. In that case also you will get small xi, small yi. Or originally you can construct a model where there is no intercept. Okay, if there is intercept as well, there will be no problem in all the assumptions, all the derivations we have done. So all the things are equally acceptable. Okay, so please check the questions from Madala which are relevant with respect to this syllabus, because in a book there are many things which we are not covering at our undergraduate second year level. Okay, so it's not that all the problems will be relevant to you. However, the problems which are related to the matters which we discussed during the class, all these things are relevant. All the tests we discussed, you can have numerical exercise during your written, during your viva, so numerical exercises in practical too, and you can face some theoretical questions. So there are different possibilities, so you have to understand the matter, so you have to practice the numerical exercises. It is not that there are a number of exercises in a book and you will be able to practice and practice. One or two problems will be there, so you need to learn the matter well. So next day I'll start autocorrelation. Today just trying to cover the rest of the part from prediction. How much we did in the last class? All these things I did, I think. So how much I covered? Do you actually know, do you want to want that I'll explain some of the parts from the prediction, or is it now understandable to everyone? So I think everybody understood everything, from the prediction part. So next day with autocorrelation, I'll discuss one or two numerical exercises. Roll number 1, Ritam, Pratyush,
Yes, ma'am.
Shoham,
Present, ma'am.
Shreya,
Present, ma'am.
Rajdeep, Shushama,
Yes, ma'am.
Goshia, Goshia is absent.
No, ma'am, she's
Goshika
present.
is
She wrote
there.
in the chat.
Okay. Sreyoshi, they are wanting absent.
Present, ma'am.
শ্রেয়সী দাস অ্যাবসেন্ট ছিল, অভিষেক,
Present, ma'am.
অন্বেষা,
Present, ma'am.
ঋতুনু, ঋতুনুকে তো আমি দেখেছি, বর্ষা,
Present, ma'am.
মেহুলি, শিবানী,
Present, miss.
সুকন্যা,
Present, ma'am.
শ্রেয়সী, সৃজিতা,
Present, ma'am.
সিঞ্জিনী,
Present, ma'am.
সিঞ্জিনী পড়াশোনা বুঝতে পারছো তো?
হ্যাঁ
শুনছো? কিছু বাড়িতে পড়াশোনা করছো?
হ্যাঁ হ্যাঁ হ্যাঁ
আচ্ছা। প্রিয়াঙ্কা, ঐশ্বর্য,
Yes, ma'am.
Shagnik, Aratrik,
Yes, ma'am.
Dhruv,
Yes, ma'am.
Lakshadweep,
Present, ma'am.
Srijani,
Present, ma'am.
Oishi,
Present, ma'am.
Ratul,
Present, ma'am.
Rupasri,
Present, ma'am.
Shayoni,
Present, ma'am.
Dibbotonu, Orko,
Present, ma'am.
Alipriya,
Present, ma'am.
Amit,
Yes, ma'am.
Yasha,
Present, ma'am.
শ্রেয়সী,
Present, ma'am.
শ্রেয়সী এখন বাড়ির সিচুয়েশন কি? একটু
Ma'am, একটু better.
একটু বেটার তো?
Yes, ma'am.
আচ্ছা আচ্ছা। স্বপ্নীল, প্রতিভু, অত্রি,
Present, ma'am.
দর্পক,
Yes, ma'am.
সমদ্যুতি,
Present, ma'am.
সম্ভব,
Present, ma'am.
okay then